Looking at section 2.6, geometric relationships. Again, we're looking at some stuff with proofs. We add a couple definitions in here and explain them a little bit. Our essential question, how can you prove a mathematical statement? So we start with 5 terms here. A lot of these we've sort of hit on, or stuff you probably already realize, but we're formalizing it because, again, we need that in geometry. So our first thing is our right angle congruence theorem. Okay. All right angles are congruent. Okay. They're all 90 degrees, so they all have to be congruent. If we're using this in a proof, you can use this. I'll normally just say that they're right angles. It's one of the things we know about right angles. Congruent supplements theorem says if 2 angles are supplementary to the same or congruent angles, then they are congruent. Okay, so if I have an angle that's 50 and I have 2 angles that are supplement to that, they both have to be 130. You can remember this as the congruent supplements theorem, but we don't use this a whole lot. So normally by the time we use it again, people forget it. So I would just state what is true. 2 angles are supplementary to the same angle, or to congruent angles. Same thing with the next one. The only thing that's changing here is complements add up to 90 instead of 180. But if 2 angles are complementary to the same or congruent angles, then they are congruent. Linear pair postulate. Linear pair, remember, is 2 angles that make a straight line. So they add up to 180. Adding up to 180 means they're supplementary. That's what this says. If 2 angles form a linear pair, then they are supplementary. Again, I would just say there is by reason linear pairs. It's part of what we know about linear pairs. And then vertical angles congruence theorem. Don't really know why we have this one. We kind of define vertical angles as being congruent, but they state it as a theorem as well. So vertical angles are congruent. And again, when I'm doing that, I would look at just vertical angles. So example 1 is just looking at using some of this stuff to solve some geometric stuff. So they asked me to solve for x and y. We're not doing a proof here. We're just solving for x and y. So here I have these 2 angles. I have these 2 angles. I have the line that crosses them. So if I look at these lines here, the 50 and the 2x minus 6 are equal, or minus 16, right? That's immediately useful. Also, 3x minus y and x are equal. Okay, that is a little bit harder to work with because I have an x in both. So we're going to solve for x here first and then see what happens. So I'm going to add the 16 to both sides. I get 66 equals 2x. So x is equal to 33. So now if I plug 33 in there, right, we have x equals 3x minus y. So I have 33 equals 3 times 33 minus y. So solve this. 33 equals 99 minus y. Subtract the 99. Get negative 66 equals negative y. Divide by the negative or multiply by the negative. Either way, y is 66. And I've solved both of those. Example 2 is trying to get us more familiar with some of the rules that we're using. Okay, so we have these statements here. We have the picture that's going along with them. And we're looking for the rules that would let us say them. So 1 says AD plus DB equals AB. So if AD plus DB equals AB. That's adding 2 smaller parts and getting 1 larger thing. And so that's an addition postulate. And I'm adding segments. So this is the segment addition postulate. Okay. Angle 1 plus angle 2, right, makes angle CDB. Again, 2 smaller things to 1 larger thing. However, now I'm adding angles. So this is the angle addition postulate. Angle 2 is congruent to angle 6. If I look, they're made up by the same lines. So that's vertical angles. Four, if D is the midpoint of AB, then AD equals 1/2 AB. Right? So if D is the midpoint then of AB, then AD is half of the whole thing. You should know what a midpoint is. It's something we've talked about before. And that's our key word. So this is definition of a midpoint. Again, when you see, I mentioned this in 2.5, when you see a key word, okay, a lot of times that is what we're using in our proof. A lot of times for my reason, I'm doing the definition of that. 5, if DF bisects CDB, then angle 1 is equal to angle 2. Okay, again, bisects is our key word here. This is definition of, and when we're bisecting, we usually say what we're bisecting, so it's definition of an angle bisector. And then the last one, ADF and FDB equals 180. Okay, that is a linear pair. If I look at the picture, ADB is a straight line, ADF and FDB together make that up. So this is a linear pair. Flipping it over, we're going to look at two proofs. So the first one, they filled in most of it for us. We just need to fill in a couple of gaps here. All right. The upside down T is perpendicular. So my given is OA is perpendicular to OC. They want me to prove that angle AOB and angle BOC are complementary. Remember, complementary means they add up to 90 degrees. So that perpendicular is very helpful. OA and O is perpendicular to OC. That is given. 2, the measure of angle AOC equals 90 degrees. That's our definition of perpendicular lines. Again, we use the key term perpendicular, even though it's not in there as a word. Right? So now I'm using the definition of that. The measure of AOB plus the measure of BOC equals the measure of AOC. So AOB, BOC, AOC. Again, I'm adding two smaller parts and getting one larger part. So angle addition postulate. Then they tell me I'm using substitution property. Well, if I look up here, what do I want to know about AOB and BOC? I want to know they're complementary. That means they add up to 90 degrees. So the measure of angle AOB and the measure of angle BOC, one, I have no way to find those, and I don't know them, so I can't substitute in there. But AOC I know is 90. So I can plug in 90. And my last step should always be what I'm trying to prove. So angle AOB and angle BOC are complementary angles. And my reason for that is definition of complementary angles. I know complementary angles add up to 90. I showed that here, so they have to be complementary. Example 4 has us working from scratch here. We're given that angle 1 is congruent to angle 4. We're going to prove that angle 2 is equal to angle 3. So first thing I have is my given. Measure of angle 1 equals the measure of angle 4. That is given information. Now, when I'm doing a proof, one of the things I want to think about is how can I get to what I'm trying to prove? So right now I have angle 1 and angle 4. I want angle 2 and angle 3. So, and I don't have a relationship there, but if I look in here, I do with 1 and 2, I do with 3 and 4. So I just start there because that lets me say something about 2 and 3. right? 1 and 2 are a linear pair. 3 and 4 are a linear pair. I could separate this into different statements. I'm going to do it as one thing. So the measure of angle 1 plus the measure of angle 2 equals 180. All right? And the measure of angle 3 plus the measure of angle 4 equals 180. That is because they are a linear pair. Now, I have 2 and 3 in there, but I want 2 and 3 on opposite sides of my statement. Well, I know these two things are both equal to 180. So if they're both equal to 180, they have to be equal to each other. So measure of angle 1 plus the measure of angle 2 equals 180, or I'm sorry, equals, we already knew that, equals the measure of angle 3 plus the measure of angle 4. Okay, that is our transitive property. Okay, they're both equal to 180, so they have to be equal to each other. Now, some people would want to sub in here. Okay, we looked at that on one of the proofs on one of the previous two sections. But what I'm going to say is, I know 1 and 4 are equal. So if I subtract this statement from this statement, the measures of angle 1's cancel, the measure of angle 4 cancel. So then I have the measure of angle 2 equals the measure of angle 3. And my reason for that is subtraction. I subtracted the 1 and 4 from the two different sides. And that is the end of 2-6.